Okay, this video is to discuss the issues with the temperature coefficients that we've been having, just kind of review and kind of clear some things up. My understanding after doing some research with some students that starting with question 7 when we went to minimum instead of maximum, that's kind of where the confusion started. So we're going to explain that, and I'm going to start with the overall picture, and I think that'll clear that up and we'll go from there. So the reason we do temperature coefficients is to make sure our solar array matches our inverter. We don't have too much power in our solar array, and we don't have too little power in our solar array to match with our inverter. So let's say we have a 600 volt inverter. I've got it right kind of big so you can see. That's how much voltage it can maintain as an ongoing process. Now, each inverter actually has a range. So this 600 volt inverter may actually have a maximum of 800 volts that it can do, and a minimum of 500 volts. Okay, the 500 volts, with that being the minimum, that means you have to have at least 500 volts of power coming through your system into the inverter for the inverter even to kick on. Once you reach 500 and go from there, then the inverter kicks on and starts transforming DC into AC. Now, after that, you have up to 800 volts. Okay, at 800 volts, this is when a fail-safe kicks in. At 800 volts for this particular inverter, the system's going to shut off. You have too much power going through the inverter, it'll burn it up, all kinds of safety features kick on. So anything over than that, then the system will shut down. Both of these, less than 500 or greater than 800 on this inverter, will cause the system to be off and you won't be getting the power from your array. Now, that is why we do temperature coefficients, because we have to calculate for the seasonal changes in temperature, whether it be winter, summer, whatever. So we look at, when we're looking at minimum voltage, we'll look at the summer, because as you learn in your lessons, as heat increases, voltage decreases. And in winter, we look at maximum, so we don't go too much power, because as temperature decreases, voltage increases. So this is the reason why we do temperature coefficients, to make sure our array, we get the most power that we can all year long. All right. So with that being said, I'm going to do question number 7 on the homework, which the question is how many 225 watt modules, each having a VOC of 42.6 volts and a temperature coefficient of negative 0.67%, so we're using percentage coefficient calculations, are needed in a series string to maintain the 620 watt voltage minimum of the grid tie inverter when the record high temperature is at 35 degrees. So that question is saying is, we know our record high temperature for that area is 35 degrees Celsius. So that's going to cause our voltage to go down, and we've got to see how much it goes down so we can make sure we have the right number of modules to meet the 625 volt minimum that we have to have. All right, so just like you did in the first 6 questions, I'm going to take my negative 0.67%. I'm going to transfer that into a decimal, so we just divide by 100, like you do normally to make it out of decimal form, and that's going to give you negative 0.0067. Okay, so now I have my percentage change, my temperature coefficient percentage. Now I have it in a decimal, so now I can use it. So 0.0067. Right. Now after that, I'm going to take the VOC for each volt. The VOC for the modules, which in this case it was 42.6 volts. Okay, so that's how much voltage, VOC voltage, that the modules are putting out. So now I have to compare that to how much they're going to change. We're getting this much change for each temperature change in the weather. All right, so for each degree we go up, 0.0067% change, well, that's decimal form, is going to change this voltage right here to 42.6 volts. All right, so now what I'm going to do is I'm going to multiply my voltage times my negative 0.0067. Okay, and I forgot to bring a calculator, so let's use the phone. When you have yours with you, Bridget, you can help if you want to. See, 42.6 times negative 0.0067 and I get negative 0.28. Okay, let's go out to the third decimal, shall we? Negative 0.285. Okay, so what this tells me is on each module, since they're producing 42.6 VOC, every time the temperature changes, or goes up in this case, the voltage is going to change by 0.285. Okay, I know that doesn't seem like a lot, but it depends on how many degrees, right? All right, so the next thing we do is we do our delta T calculation, our change in temperature. All right, so delta T, you may see it as for our science people. So delta T in this case, we have 35 degrees Celsius. Yeah. So remember, the first number we put in is 35, or the temperature that it's going to be. And we look at the temperature, the lab temperature, right? So that is 25 degrees Celsius. And that's going to give us 15 degrees. I'm sorry, 10 degrees. Not bad. All right. So now I see what my voltage change is for temperature, V over C. And now I've got my how many degrees I'm going to change in Celsius. So now I do my plug and play. So now I take negative 0.285 V over C, and I times that by 10 degrees Celsius. So if we look at this, the V over C is actually voltage over degrees Celsius. So now we know just by mathematical algebra that our degrees Celsius is going to change, and we're going to be finding volts. All right. So negative 0.285 times 10 degrees and I always do it just to double check. That's going to be a negative 2.85 voltage change. Okay? So what does that mean? That means in this situation, every time the temperature goes up 1 degree, I'm going to lose that much voltage. Okay? So now, I add my 42.06, because we're still kind of calculating for each module now. So 42.6 VOC, so volts. All right. Now, in the max formula, it was adding, but since we have a negative, we're actually going to be subtracting. Okay. So 42.6 volts minus 2.85 volts.
39.75.
How much?
39.75.
All right. 39.75 volts. Okay. What does that mean? Well, that means now each module at 35 degrees Celsius, each module is only going to be producing 39.75 volts instead of 42.6. Okay? So now we look at our minimal voltage that we have to meet. Okay, so 39.75 is the number to remember. I'm going to erase all this. Alright. So each module is now only going to be producing 39.75, and I know it's probably hard to read, but that's how many they're going to be producing. The question asks, how many 225 watt modules will we need? Okay, the 225 watt modules is just to classify the modules as kind of a teacher way to be mean, I guess. It's information you don't need. Alright, so
we
figure that out. Okay. Alright. So the minimum voltage I have to have is 625 volts. That's how many volts I have to have for the module to kick on. Alright? So 625 volts. Each module, for the 225 module, each module is only going to be able to produce 39.75 volts. So we divide, right? So divide by 39.75 volts. And now we're probably getting the short rows. Everybody kind of knows what's going to happen next. Alright, so 39.75. So let's do this. let's take 625 divided by 39.75 equals 15.72. All right. So that means I can have I have to have 15.72 modules working at this temperature because they're only going to be producing 39.75 volts. So 15.72 modules will kick on my inverter, will give me the 625 volts I need at the 35 degrees Celsius. But since we're looking at minimum, instead of rounding down like we do during the maximum, we round up. So this is actually going to be 16 modules. That's how many modules I need in my array to make sure I'm getting the 625 volts that I need at 35 degrees Celsius in temperature. And then it's just rinse and repeat for the rest of them. And do the opposite for the maximum, but I think everybody figured out the maximum. So, I hope this...
Maximum, you go down, you would go down?
Yeah, maximum you would round down. So we were looking for maximum, and I could only have 625 volts. Then instead of 15.72 and round up to 16, I actually round this down to 15 modules. That way I've got a buffer and I don't go over. Now, of course, the calculation is going to be a little bit different because you're not going to have some negatives where you have negatives in this calculation. And you're going to have some negatives where you had positives in this calculation. Okay? That makes sense?
Mm-hmm.
All right, cool. So I hope that helps. If there's any more questions, let me know. If you need me to do an example of a maximum voltage one, I can do that. All right? Thanks.